Scientists are using lasers to redirect lightning. Lightning rods are limited and rockets are impractical. High-powered lasers offer a continuous and effective solution.
Okay, confession time. I love thunderstorms. The sounds, the flashes of light, the ground rumbling. I love all of this when I'm indoors. But when I'm outside in the rain and seeing lightning coming my way, I, a full-grown adult, become terrified and run into the nearest building. I've been that way ever since I can remember. And Aurélien Roy, a physicist at École Polytechnique near Paris, says he was the same as a kid.
I think like many kids, I was at the same time scared and fascinated by the lightning and thunder, by the big flash of light that you see and waiting for the sound to know if it's far or if it's close. My dog was always frightened by the lightning and shaking like this.
And lightning doesn't just scare dogs and kids. It has real-world consequences outside of raising our heartbeats. Storms delay flights, lightning strike buildings and wind farms. People get struck by lightning every year. Between 2006 and 2021, 444 people in the United States died from a lightning strike. Aurélien and his multinational team are on a mission to draw lightning away from planes, people, and other precious objects. And it turns out, despite a brief flirtation with rockets, scientists' starting point is technology that's over 250 years old.
What we have for the moment as a solution to redirect or to protect from lightning is the lightning rod invented by Benjamin Franklin a few centuries ago. And actually, this is the only method that is known to be efficient to protect against lightning. But it's most of the time limited to a few meter height.
Basically, the big technology we have to defend ourselves against lightning is a big metal rod that, when placed on top of a 3-story building, covers about a 10-meter radius, or roughly 33 feet.
The range of action of this lightning rod is relatively limited because it corresponds roughly to the height of the lightning rod.
And there's only so high up you can reasonably build a lightning rod.
Today, nobody is using a kilometer-sized lightning rod because it's too complicated to generate, to produce, and to install.
Plus, these days, we have huge buildings. I mean, this method can't even protect an airport. And past or present, there's large swaths of land that are unprotected. It's a problem in need of a 21st century update. Today, we revisit this beloved show on lightning, how it works, why rockets are not the answer, and how high-powered lasers could be the key to protect the world from dangerous lightning strikes. I'm Regina Barber, and you're listening to Shortwave, the science podcast from NPR. To solve the problem of how to redirect lightning, researchers first need to understand what lightning is. The easiest way to think about this is if you've ever scooted across a carpet with fuzzy socks on, and then you shock yourself on a doorknob, or purposely shock your sibling. There's a little spark of static electricity. And basically one of two things is happening here. Either you're accumulating electrons, those negatively charged subatomic particles, on yourself, or electrons are being ripped from you, making a part of your body a supercharged thing, where before you were more or less neutral, no big charge imbalance. In either case, your body wants to be balanced again. So that imbalance of electrons results in these subatomic particles literally jumping off your body, or to your body from somewhere else. That is mini lightning you see as you shock yourself. As for what that means for lightning out in the world, that's what's happening to the clouds in the sky. Water and hot air currents move those electrons around.
Lightning happens when you have formation of huge clouds in the sky with a charge inside the clouds. And actually, the charge appears in the clouds when you have a big movement of particles of water in the sky. And because some spaces are hotter and some are colder in the skies, you have some air that goes up and some air that goes down, and it makes friction. And it's like when you touch a sweat, no, the wool.
The wool sweater.
When you touch it very fast, you can make electricity.
The clouds become charged, and electrons either want to travel to the ground or connect with a positively charged cloud. That's lightning. And while it's very unlikely that lightning will hit a person, every year it damages trees, buildings, and delays many flights. So what's used now to redirect lightning away from buildings is a lightning rod. It's a pointy piece of metal that acts as a conductor, letting electricity flow through it. And it's connected to the earth, or grounded. Since the rod is grounded, it can attract lightning and siphon off excess charge from the clouds, reducing the likelihood of lightning. Aurelian says that there's technically another method that successfully redirects lightning: rockets.
In the end of the 20th century, the fact to use rockets with an electric wire attached to the rocket. So if you send a rocket with a very long wire behind the rocket, 100 meters or even more, the rocket with the wire will start to be charged in the presence of the electric field created by the lightning cloud, and it will induce a lightning and guide it along the wire. So you can have a guiding of the lightning like this.
But this rocket approach has a lot of downsides.
It requires a very precise timing to shoot the rocket, and also it can only work one time. So it was never really considered as a protection for lightning because it's too expensive. It's waste and it can fall, you don't exactly know where. And you have to retrieve what remains of the rocket. But this is basically what we want to do with the laser, but with something that doesn't fall down and that you can use continuously when you need it.
So, okay, lightning rods cover too small an area, rockets are impractical, enter those high-powered lasers. In 2021, Aurelian and his team successfully used a laser to redirect lightning for the first time ever. This is how it works. The laser shoots a beam into the air, and it forces molecules in the air to undergo ionization.
In every molecule in air, you have nitrogen and oxygen. You have some electron around the molecule. And if you send energy on this molecule, you can detach some of this electron outside. And then the electron can go everywhere.
They used a laser that pulses 1,000 times a second, which basically creates a column of air with all these free electrons, turning it into a giant lightning rod. This experiment was done on a remote Swiss mountain, where a telecommunications tower is struck roughly 100 times a year.
So on the Swiss mountain, the difficulty of this station was that it's not accessible by road, so you need to use a gondola to go there, or to use an helicopter. And so we used the gondola for most of the equipment, but for that we had to design a laser that would be able to be splitted in small parts to fit in the gondola.
It took 4 months to install everything.
So we had to separate the laser in several parts, to put it in the gondola, and to make the laser in one part again on top of the mountain.
It was an exciting moment, because this laser, it's a fulfillment of a decades-old idea. But a successful test wasn't possible until recently due to a number of things. First, the lasers had to get more powerful.
We choose a laser technology that is able to shoot 1,000 laser pulses per second. So it's a big increase compared to all the experiments that were done before, because they were only shooting 1 shot per second or 10 shots per second. So we have much more chance to catch the lightning when it's developing and to guide it during its propagation.
Second, it turns out it's really hard to predict where lightning is going to be to test these lasers. Aurelian's team found a solution for that too.
We choose the place where the lightning happens often every year, about 80 or 1,000 times every year. And more important, all the time the lightning is hitting the big tower that is installed on top of this mountain called Mount Sentis. So we can be sure that for all these lightning events, we know where the lightning will go. Even if you go in a country that records thousands of lightning every year, this lightning can be 1 kilometer or 2 kilometers away from the position where you are.
But the challenges don't stop at laser power and lightning prediction. There's also the disruptive temperature changes and the many ways the field site is impacted by all the terrible weather associated with lightning.
You have a very strong wind during the lightning storm, up to hundreds of kilometers, a lot of rain also. And also you can have electricity shutdown during the lightning. So we had to face all this difficulty during the experiment, and it took us also 1 month to make the laser continue to work.
And because they had to be at the station when the lightning storm was happening, they had to sleep on the mountain right next to the tower.
So at the beginning, we were trusting that the weather forecast could tell us precisely when the lightning will come. But after a few weeks, we realized that the forecasts were not very precise and that the weather was changing very fast. So after this, we decided to stay all the time on the mountain and to sleep on the mountain. So every morning we had to start the laser. We have to estimate if there is a chance of lightning, then to call for the airport to say, we will use the air corridor, so please be ready to stop the air traffic. And then we have to confirm 1 hour before shooting to stop the air traffic, and we can start to shoot the laser.
In the study, the laser was able to protect a whopping 180-meter radius, which is why Aurelian thinks lasers have a lot of promise, and he hopes to one day extend the laser way higher, hundreds of meters in the sky to protect an even wider radius. But that will require more data and probably more mountaintop lasers in more places around the globe. It's a feat that will take careful planning and probably years to accomplish. In the meantime, I'll be happy looking at lightning, knowing that my irrational fears are one step closer to being put to rest. Thanks to science.